your classes, and they're to record what is being taught for the benefit of the online students. And is it recording? Okay. It's on HD or FHD? Huh? Is it on HD or FHD? HD. Good. Thank you. Let me see what the field of view is. I think I want this closer. Over here somewhere. Mostly we'll use the whiteboard. Make sure not to drop it. That would not be good. Okay, that's good. Can you see the board still? It's a little bit in the way, I know. Maybe I can put it like there. Something like that. Okay. Am I out of the picture? Where? Is this in the picture? Half. Okay, so it's really just the board. Okay, that's fine. So, yeah, so Clement is, oh, and why is he, so he's a distance student normally.
But at that time when I had my phone, my lecturer was there. She was moving. I think it is.
Is that right?
So when we were talking about
so he's here for a few weeks.
Materiality, we're thinking those lines.
4 weeks.
To say which you value that it's very important.
2 weeks. So I invited him to join the class.
That's why we are saying about
and then continue
to say
back home in near Nsanje.
Materiality is very, very important to us because then you are going to
very nice village. You should go visit.
This one is fine. Even organizations do the same. They will say
let's talk about
that
some calculus.
If an organization uses,
any
let's say 50,000
questions
below,
since I've given you your problem sets, you had a chance to quickly look. Do you have any?
But if it's more than that, they're going to be no.
Something. That
please press on Mrs. Pagat. She has to recover that money.
What?
Okay.
Projector?
Even yourself, you can do the same. Huh? Your daughter or your sister has taken your money.
Oh, you want to check? Okay.
Misused it.
Let me see.
You can't be the same.
By the way,
you know.
I still didn't get a
even people are going to get
the class average for the first problem set was 81%.
The 1 million that you
for the second problem set was
while
actually, sorry, the first problem set was 1.1.
Please don't do that again next time.
1%.
You have to give me back.
And 1.3 was 63%. So we're going.
You know, it's 30,000. Okay.
We want to go back up.
It means to you, what is material is.
And as I said, I think most of the reasons.
So this is exactly what we are talking about when we are talking about
material. You just didn't answer all the questions. So when you answered the question,
so timelines.
But if you don't answer
timelines that the book specifies to us.
Should I give you grades for not answering questions?
In connection of presentation of financial statements, according to our topic in the course outline, if the publication of financial statement is delayed too long, after the reporting period, they are beautiful to be
oh, you know what I could do?
The standard, meaning standard, international standard number 1, that is what they are saying. Standard states that entities should be able to produce their financial statements within 6 months of the end of the reporting period. Okay. So,
which problem set do you want to ask questions about? 1.3 or 2.3?
This is what we are talking about.
We're going to
this, Dorothy, mind you,
quickly
the same form.
Relocate this to see the projector. That's the beauty of being portable. By the way, this needs to be straight. Huh? So I'm just going to turn off that light so we can see the. Excuse me. Okay. Here we go. You just make sure it's set up properly. Oh. Okay. So, well, which problem set do you want to ask about? Which section? Which section? 2.3. Has everybody submitted 2.3? That was due today. I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. One person is not submitted, which is okay. Okay, ask. I may or may not answer. I don't need that. Hi, where's the toolbar? Oh. Mm-hmm. 7. Right down. 7, D and E. Okay. So how do we think about these? Let me ask, did anyone else have trouble with these ones? Or ask another way, you had trouble with it? Did anybody do it? And turn off my phone here. Did anybody not find it difficult? You found it, easy or doable? Did anyone attempt an answer? Loveness. What did you get for an answer? What did you get for an answer? Or how did you do it? Here, you want to come do it on the board? Is anybody here studying journalism? You want to practice being a cameraman? You might have to get closer. Turn that around. Okay, that's kind of a bit of both, I think. Can you explain what you did? Can everybody see? Charles, can you see the board? Yeah. So, Loveness, explain to us the steps, please. So this is we have to write down the value of How do we read this, first of all? How do we read this? It's the logarithm in base b of the square root of b. Okay? So the next step, she wrote b to the power 1/2. Why? The square root is the same thing as the half power, right? Everybody know that? All right? And then, how did you do this step? The 1/2 goes away and it shows up in front. Why? Huh? The rules. What rule? Inside the logarithm, a power can come out in front of the logarithm and multiply it. So this is now a half times the logarithm in base b of b. Right? And then the next step is, oh, we've completely lost the logarithm. What happened? How did this become 1? Charles, how did that become 1? Is this a rule? This is the definition of the logarithm. We should know this because of when I write the logarithm in base b of a number m, and I say this equals n, then this is the same thing as the base b equals something is the power and something is the result. What goes, is this m or n? And this one is m or n? You know? I'm sure you know. You don't know. If we have the logarithm in base b of a number m, so in this case we had square root of b, but whatever it is, it's m, and this equals n, that's, I can say the same thing. This mathematical relationship is the same as b to, put it like this, right? There's b, the base, to some power equals something, right? There's an m and there's an n. So one of them is here and one of them is there. Which one goes where? Think about it for 15 seconds, and then we will take a class vote. Is the question clear? It's clear, the question? Okay. Okay, so who thinks this is m? Raise your hand. Who thinks what? This, the exponent of b, is m. Okay, you think it's m. Who thinks this is n? That means everybody else. You didn't raise your hand. You think it's n? M or n? Still not sure. M or N? You don't know? You know? M. Okay. Linda? M? Okay. And Charles? What goes here? M or N? M. So we have 3 M's, 2 N's, and some I don't knows. Okay. The answer is, let's use this word. Why? Because this is the definition of a logarithm. You just have to know this. You have to learn it. So when you have, I'm going to just take out the dotted things now. This kind of statement, you understand, right? A number raised to a power equals another number. Clear, right? We don't know what the numbers are, but whatever they are, this is true. That some number b to the power n equals m. We're happy?
Yes.
Okay. Now, when we get to the logarithm, we are asking ourselves the question, is this? We have the question, suppose I tell you I have b, and I want to equal m, yeah? Ooh, I know. Well, okay. What is the exponent that would give me m? Right? This is now your question. Right? And the way you find that is we say, okay, then that's, I know b, I know m, but I want to find this. Here, I know b, I know n, now I calculate and I find m. Right? But maybe what I know is b and m, but I don't know n. So now I need to find n. And that's what the logarithm says, if I know b and I know m, then this operation gives me n. Questions? I want us to think about this idea that I know something and I'm looking for something else. I'm going to erase this now. This might sound like, why would I be asking this? Who wants to know this? Why is this useful? Right? And if I say A plus something equals C, is this something we're interested in? So, for example, this morning I had 2,000 kwacha in my pocket. Yeah? And now I have 800 in my pocket. So how much did I spend? Well, I must have spent 800 is what I have, plus 800 is what I gave my friend, maybe. And together, this equals 2,000, right? So I started with 2,000. Now I have 800, so what do I have to add to 800 to get 2,000? Yeah? And the answer is C minus A equals this thing, right? So we have created a new operation, which is subtraction, in order to answer the question, what do I have to add to A to get C? We had the addition operation, But by simply saying, instead of saying A plus B equals what, now I say A plus what equals C. And by asking this question, I have created the operation of subtraction. Like, why do we need subtraction? Well, we need subtraction because we want to answer this question. Sometimes this is what life presents. Right? So it's a similar thing of, okay, b to the power n, and then I'm looking for an answer. That's like this one. I have an operation, addition, I take two numbers, I add them, I get a result. Here I have two numbers. Now the operation is not addition, but exponentiation. That's a big word. You know the word exponent. Exponentiation is the operation of raising a number to a power. So now I have two numbers. Instead of adding them, I exponentiate them and I get a result. Similar to this, right? But now I can, the same way that I turned this one, I said, instead of asking what is the result, if I give you the result and I ask what is the other number, I can do the same thing here. And ask, if I give you this number and the result, then what is the exponent? And when I ask this question, it creates a new operation. Just like this one created subtraction. Now, this question creates the logarithm operation. The logarithm operation is what answers this question. You see? Right. And therefore, so we were trying to answer, why did we start doing this? Is because we had logarithm base b of b, and Loveness said this equals 1. Is that right? Okay. So now, can we think about this? Now that we know this, how can we rewrite this like that? What would we write? In this form. So we want to take this logarithm and we want to write it in this form. What would we write? B is equal to what? B. So the base goes here. Yeah? This one is the m. Where does the m go? It goes on the other side of the equal, so it goes here. Where does the 1 go? It's the power of b. Is this true? B to the power 1 is b?
Yes.
Yes? So when we don't know, when you're given this, you go, oh, what is this? Then you would write, okay, b goes here, b goes here. What is the power that makes this true? Here's 1. Does it matter what this number is? Like if this is, right, b is a number. Yeah? So if this is 2, if I write logarithm of 2 base 2, this is equal to 1. Okay? How about the logarithm of 3 base 3? We would have 3 equals 3, and the power is 1. So that also equals 1. Okay, how about 1/2 and 1/2? It's 1. I have one voice saying 1, everybody else is quiet. Does that mean agreement? Or, what is this equal? Half? Oh, now we're getting some different. Half? 1? What else? 1? Why? Linda, can you help us? What would we write to put it in this form? So this is equal to something. Make sure we can read it properly. Logarithm in base 1/2 of a half equals what? How do we write this in this form? How do we write this in this form? What goes in this place? I'm asking Linda. What goes in this place? What number? One? 1/2. This is this one, right? Which is this one. So what goes here? 1/2. Okay. Now, what else are we going to write? Equals. We're writing this form. And we have something here, which is the m. Linda? Where does it go? Where does this half go? In here. So you compare. You look at this. Let me use some colors here. I'm going to use my 3 colors. It's going to get very exciting. Okay, so we have log base b, b goes there, of m, and m goes there, and n, and n goes there. Yeah? So now, let me clean this up. We have log of 1/2, that's the b part, and then of 1/2, and then equals something. Something, I guess, should be in red. So now we're writing this, which looks like that, in this form. Okay? So when you look at this 1/2 comes here. It's like this one. You can even put it in brackets. Where do we put this 1/2? On the other side, okay. 1/2 goes here. What's left? What are we missing? How do we make this? We need the red one now, right? Which is up here, the exponent. What number should we put here to make this true? Are you sure? Are you very sure? Yeah? 1. So 1/2 multiplied by itself once is 1/2. So any number you put here, if it's the same number in the base and in the argument, this is the argument of the logarithm, you get the answer 1. Always. Are you sure it's always? What if I put a negative number here? Is it still 1? Like, let's do an example. So we're done with a half. Thank you, a half. We appreciate your service. So now we don't know if it's 1 anymore. So now, if I give you -4 and -4, so we have -4 here. I didn't change the colors, but anyway, -4 here. What's the exponent? It's still going to be 1.
Yes.
Does it matter if I change the 4 to another number? If I make 4 another number, if I make 5, -5, -5, -100, -100, it will always be 1. So, have we convinced ourselves that the logarithm of a number with itself as the base is always 1? Yes. Okay. Now E, so that was D. This discussion came out of D, right? What about E? What is the issue with E? Now you should all be able to do it. So let me write it down. It's the log base B of 1 over B. Right? Is that what it is? Yeah. Right? Yes. Okay. I should put it over here so these guys can see it. Do we still need this? No, you know it now. Okay. Okay, I'll just rewrite it closer to you guys. Log base B of 1 over B. Now, how do we simplify this? So, we know that in the laws of logarithms, red doesn't show up very well, I don't think. In the laws of logarithms, we have seen that the log of a number a to a power n equals n log a. Yeah? This is, let me just write it here, log a to the power n. This is always true, right?
Yes.
So, and we know, we have just proven that log base b of b is 1. So we see a b, and we see a b, and we think, oh, wouldn't it be nice if we could do this? Can we do this? Yeah? Is this the same as this? Is b the same as 1 over b? No. Can we make them the same? How? By doing what?
Power of powers. That will be
That will be what?
exponential.
You want to write down what you're thinking? Actually, use the blue, it's better. Okay. Can you write it bigger so that they can see, and then explain? So what did you just write down? How do you read that?
It's log b power -1.
Log base b
Yes, log base b
of
power
to the
-1.
power -1. Do we follow this? Yeah? Okay, what's the next step then? Think, don't do it yet. Think, what is the next step to simplify this?
Make this B a number, then equal to B.
Come, yeah, do the next step. We'll take turn. By the way, Justin, when we're doing a derivation, we would put equal. Yeah, each step equals the next step. So, thank you, Justin, for the following step. If we made that substitution, then what would happen? Can you, they can't see because you're standing in front of it, so you have to. So, James is proposing a substitution. If b equals 1 over b, then what would be, how would you write this now?
This.
Yeah. This is not derived from here. You have suggested, this is like on the side here, you're saying if this, yeah, then this will be equal to what? So we have log base b, and you're saying if b to the power minus 1 equals b, then I can replace this. I could just write b. Yeah?
No. No, it hasn't reached that way. This was just the next move I was thinking about.
What you're thinking of is a substitution. You're saying if I assume, right, this is true, but this does not follow from this. This is a new statement. This doesn't imply this.
Okay.
Yeah?
I thought you said if log b number m is equal to n. This can also be like this. So since here the n is silent. Yes. So when it comes to this, I thought we can put the power in here, but I don't know how to make them.
So if you put, okay, I see where you're going now. Okay, we're rewriting it in the other form. Fine. So, thank you. You can stay if you like, or you can sit. Okay, this was helpful. I needed to understand where you were thinking. So you remember we were saying if I write a logarithm, it means the same thing as if I write it like this, right? This, we remember that. So what James was thinking is, well, I have the base b, so I'm going to put the base b. I have this b to the minus 1, and it goes on the other side of the equal sign. Now, what I'm looking for, this equals something. I don't know what yet. I'm looking for what it is. I'm looking for the n. I don't know what the n is. So somewhere here, there has to go a number. And that's the question. What is that number? So what goes here? To make this true, what goes here? Unknown letter. But look at it. You can, it's not unknown. You know what it is.
Make it negative 1.
It's negative 1. B to the negative 1 equals B to the negative 1. Right? So this is equal to negative 1. But there's another way we can get there. That's one way to get there. This works. Another way to get there is to use this rule. Yeah? How would we use this rule from here? Ishmael. How do we use this rule in here? So this equals what? This equals, how do we use this rule here? So here we didn't write the b's, but the base can go there. Do we have something that looks like this? What are the pieces? So we have the log, yes. We have a base, yes. What is the a and what is the n in our case? A is? A is b, and n is? So we can write it like this. So we take the negative 1 and we put it in front. Times the logarithm, base b, of b. Not power b, just of b. The logarithm of b. This is how you read it. The logarithm of b in base b. Or the logarithm of a to the n in base b. It's the logarithm of something. Right? This is true?
Yes.
Can we simplify it further now?
Yes.
How?
That logarithm of b is b1.
Mm-hmm. Because the exponent of b that gives me b is 1. So I have negative 1 times 1, which is equal to the same as when we thought of it this way. So it's good, we get the same answer. Suppose, now that you know this, any questions about this? Do we understand the logic? Loveness, yes. Linda? Somehow? You'll need to spend some more time thinking about it. Clement? Are you with us? Does it make sense? We'll do some more study. Charles, you okay? All right. Most of us are okay. So, new problem. Now that you know all this, what if I have 1 over b squared? Everybody, let's take 2 minutes. I'm going to leave this on the board. You can use it as a guide. Solve this. It has a very simple answer. What is it? I'm gonna get something from my office that will help us for the next part. Okay, how we doing? Who's still working on it? No, you're doing good. You're doing good. Thank you. You did what I asked. Don't be sorry. Don't be sorry. Is anyone still working on it? Or everybody has reached something. I know you find it maybe comforting to have a phone in a math class, a calculator. You're using it as a calculator? Okay. Calculus does not need a calculator. If you do, I will tell you. You do not need a calculator in calculus. Calculus is about thinking, not about pushing buttons. You're not doing arithmetic, you're not doing accounting and adding lots of numbers. You're thinking. No, not even. You're now at a level of math where we use letters. We don't use numbers. If we use numbers, very simple numbers, the number 1 is a simple number. Do you need a calculator for the number 1? The number -1? The number 2? Oh, big number. Oh. You don't need a calculator for these kinds of numbers. So, when I left you with this problem, what do we get as an answer? This is to apply what we have just learned. We just went through the whole explanation, so now we want to take together what we have learned, what we know, and see if we can apply it to solve a new problem. It's a good way to test your understanding. And if it was hard, then you go, okay, where was it hard? Don't just say, the whole thing was hard. No, I was stuck at this step. Yeah, I don't know what to do after here, or I don't know what to do after, Then you ask your friend to say, what is the next step? Don't ask what is the answer. What is the next step? And then your friend can say, think of this. You go, oh yeah, now from here, now I see. Oh, now I'm stuck again. Okay, what do I do in this step? Ask for help don't just ask for the answer. Ask for help. What is the next step? So, yes?
Is that B of Chan or
Chan? If I say yes, will it answer your question? What? How to read this. So, this is the logarithm in base b of 1 over b squared. Yeah? So, 1 over b squared. Who has an answer? Or thinks they have an answer? What is your answer? -2. 1. Okay. -2. Mike, what did you get? -2. -2. Loveness? Okay. -1. 1. -2. So mostly -2s, but some 1s and -1s. So, shall I... How did someone solve it using this? Yeah? Okay, can you show us? So equals log base b of b to the -2. Okay. Is -2. Keep going. Show the steps. What's the next step? It's the right answer. But show more of the steps.
I use the rule.
You use 2 rules at the same time. Use 1 rule, then in the next step, use the other rule. So which rule will you use first? Can you use this rule? from log base b of b to the minus 2. Can you use this? Not yet, right? B to the minus 2 is not the same as b. So maybe we can use this one. Okay. Do these, can you see? Loveness, can you read this? Do these steps, can we follow these steps? Is this equal to this? No. This is not equal to this. Oh. What happened? This was on the right track. Minus 2, if we use this rule, so you know when I tell you to show your steps, show your work, this is what we mean, right? In every step, you do one operation. And then in the next step, you do another operation. So here, we're going to use this. So what we have here is minus 2. So minus 2 should come in front. But then we still have this. So now we still have log base b of b. That's the first step. Now that we have this, we can use this definition. Now we don't write that this is equal to this, but you can say use this, right? And now that is equal to minus 2 times 1, which is true. Log base b of b is 1, and therefore the answer is negative 2. Now, let me also point out, I'm going to erase these now, that whenever you do a math problem, if you're not quite sure whether you got the right answer, and even if you think you got the right answer, you should check your answer. You don't have to wait for someone else to check it for you. You can check it yourself. How do we check our answer? We can put the result back, right? In a way, this is equal to x. And then we're asking, what is x? X is what? Right? Then we say, we think x is minus 2. Okay, so let's put our answer for x, and then check, is this true? Yeah? We check our answer. So let's say log base b of 1 over b squared equals minus 2. We want to check if this is correct. Now, have you learned this rule yet? B to the power of log of a base b equals a. Was this in the rules of this section? B to the power of the logarithm in base b of a is a.
That's true, but we did.
It wasn't in the book? Okay. We're going to need this in order to simplify this one. So let's quickly, or not quickly. So we've done our derivation. We got x equals minus 2. We'll just keep that there. And now I claim, and you can believe me or not believe me, that this is true. Now, can I prove it? In math, someone claims something, you say, prove it. I can prove it. So we said, we know that the definition of a logarithm, log base b of a equals, what do you want to call it? C? Let's call it C. Yeah? And this means that b to the power c equals a. Yeah? So I have b to this power, log base b of a. Log base b of a, I can call it c, right? So this is equal to b to the c equals a, which is the definition of the logarithm. Therefore, this must be true. Because what this says is, what is the exponent of b that gives the result a? The result a for this is the exponent of b, which is, this is the exponent of b. So what is it? It is exactly this, makes a. So this is true. Okay? So we're going to use this now. So I'm going to take, remember, if we do something to both sides, then it's still true. So I'm going to take b to this power and b to this power. You maybe have never seen this before. You're allowed to do this. Yeah? If I have 2 equals 1 plus 1, then I can say 2 to the power 2 equals 2 to the power 1 plus 1. It's true?
Yes.
If this is true, then this is true. Yeah? They're both true. So from here, I'm allowed to do this. And it doesn't matter what number I put here even. I could pick any number. I could put 100. It would still be true. Right? I could even take a negative number. I could take a fraction. I could take minus a quarter to the power 2 is minus a quarter to the power 1 plus 1. Still true. So you are allowed to take the two sides of an equation and make them the exponents of the same base. Of course, the base has to be the same, otherwise it's not true. Right? So that's what we're going to do here, and we're going to use b. Now we have b to the power log base b of 1 over b squared equals b to the minus 2. And now we're going to use our new relation. So we say b to the power log base b. It's important that the bases are the same. This doesn't work if the bases are different. This only works if the bases are the same. So that's why I had to choose b here. I couldn't choose anything. I had to choose b to have the same base as that. And then all of this is equal to 1 over b squared. Right? With me? So 1 over b squared equals b to the minus 2. Is this true? Is this true? So if this is true, then this must be true. If this is true, then this must be true. And if this is true, then x must be minus 2. And our guess, or our answer, is correct. We have checked that it is correct. And you can do this with whenever you're given problem, almost always, you can take your answer, put it back in the original equation, and check that it satisfies the equation. And if it doesn't, then you go, oh, I must have made a mistake somewhere. Let me check my work. Okay. So this was a demonstration of, it's important to check your work. Depending, if it's a very simple problem and you're very sure, fine. But if you're not sure, then check. It takes a few more A little bit more effort, but it's well worth it. Let me check the time. Okay. I want to, before we go on, I want to say a word about why would we be interested in logarithms? Besides that, okay, it's needed for math and calculus somehow, but why in life will it come up? So, you all know about interest on loans, right? Or on an investment. Charging interest? We know. So, if you say you're going to invest some money, how much money are you going to invest? Pick a number. $6 million. Okay, we have 6 million. And and we're going to charge, or not charge, but you're going to get how much interest? What's the annual interest percentage? That's not a percentage, that's an amount. I want a percentage.
2%.
2%? 3. Okay. 3%. How do I calculate how much I'm going to have at the end? I would say times 1.03, right? 1 plus the interest rate. 3% is 3/100ths, right? And the 1, so I'm going to have my investment, that's the times 1, plus the interest on the investment. So together it's this times 1.03. This gives me how much money I will have after 1 year. But now let's say you don't need the money for 10 years, right? So every year you get interest and then your investment grows. Then you get interest on the new amount, right? So after 1 year, I now have, so what's 3% of this? 6180000. All right? 3% is 3 times 1%. 1% is 100th. This is 100th. I just go, right, take away 2 decimals, right? And 3 times this is 18. So I have 180 is my 3%. Told you you don't need a calculator. Okay, after 1 year I have this. Now again, I get 3% the second year. And then I get a new number. I'm not going to calculate every one of them. But every year, right, whatever number this is, this number went here. This number times 1.03 equals something. And every time we multiply by 1.03. So in other words, I could say I have my 6 million principal and I multiply it by 1.03 times the number of years. Maybe n for number of years. Yeah? After 1 year, it's 1.03 times this. After 2 years, it's 1.03 times 1.03 times this, and so on. Right? This isn't logarithms yet. Logarithms are coming. And this will tell me, this is how much I have after n years. It's a very useful formula. In fact, you can write it even more generally, and maybe you've seen this already in some of your other courses. You have a principal, here we have 6 million, times 1 plus your interest rate r as a decimal, so we have 0.03, but r can be whatever, to the power n. Sometimes it's t for time. Right? So that's our formula. Now, if I tell you that you're going to invest 6 million, or you tell me you're going to invest 6 million, you know the interest rate is 3%, and you would like to have 8 million. Yeah, you're starting with 6, you want to reach 8. And now your question is, how many years do you have to wait in order to have 8 million from your 6? Is that a reasonable question? Yeah, and you would want an answer. So someone comes and says, I have 6 million, I want to reach 8 million because some reason. And you say, okay, I know the interest rate is 3%, so how do I calculate the exponent? This is what I need to find. And therefore, I need a logarithm. I say n is the logarithm in base b, so 1.03 of, now we could say, you want this, if this is 6 and this is 8, then 8/6 of p is 4/3. So you want to reach 4, I'm going a little bit quickly here, but 4/3. You want this to be equal to 4/3, and 4/3 times 6 million will be 8 million, right? So this needs to equal 4/3. That's the person's goal. You know the interest rate, you need to find the number of years. And in other words, what you need is the logarithm. So logarithms are not just some mathematical idea that for some reason they make me learn, but I will never use it. No, you're going to use it, aren't you? Okay, so that's just one example of where in daily life, this would be investment, banking, loans, anything where there's a kind of compound interest. Or if you're in biology, any kind of exponential growth, you will end up calculating logarithms. And maybe you will use a calculator when you put the actual numbers, but you have to understand what is a logarithm because it's what helps you find the answer, right? Is your brain... All right. I was going to start or move into our actual calculus stuff. So let me take a moment here and show, where is it? So in our course outline, the first topic is meant to be limits and continuity in this introduction to calculus. This is now week 4 of the semester, so we're just over a quarter through the term. And we have not yet started limits because we were doing this review of some algebra because we need to be strong on algebra to be able to do the rest of the course. And so what I want to introduce now is thinking about your problem set from last week involved graphing, especially linear equations, right? And you had many problems where if I give you an equation like y equals 2x plus 2, and you were asked to graph this, right? How would you graph this? All right, so we have axes, first of all. We need some units. Now, how do we go from an equation to a graph? What's the first step?
Find the coordinates, like graph.
Coordinates, okay, like what?
When x is y, what is value of y? When x is 1, what is the value of y?
So we could put in different values of x and find y, and we would put points, and that would give us the line.
Yeah.
Okay, that's one way. So we could make a table. So we could say if x is 0, 1, 2, what is y? So that's one way to do it. It works. Another way to do it is to look at this and say, oh, I know this. This is a linear equation. It's called linear because it's the equation of a line, right? And the line has this kind of equation. We know has a slope and an intercept, right? So does that help me graph? If I don't even tell you the equation, yeah? Let's say you don't know this. All I tell you is intercept equals 2 and slope equals 2. Now what do you do? Now you can't plug in x and y. Of course, you could look at this and say, oh, I know the equation for this, and you could write the equation, and then you could make the table. But you could also say, okay, intercept is 2, that's here. I know 1 point. That's what it means to be the intercept, right? Where x equals 0, it intercepts the y-axis at 2. And the slope is 2. Okay, so the slope means if I go over by 1 unit on x, then I change my units for y is 2. So if I go 1 on x, this is 1 from here to here, right? Then I have to go, this is positive, so I go up. This is 1, this is 2. So there's my second point. And now I can draw a line. And there's my graph, right? Not sure? This is not how you think about it? Sorry? I wrote the wrong class. Where did I surprise you or lose you? Did I lose you?
Because this question, because the slope is positive, so let it go 2 steps up.
Yeah.
If you take 2 numbers up, what if it was the slope was negative?
What do you think? Why do you think it's called the slope? In your everyday life, what is a slope? Don't think about math. What is a slope? It's a hill. Yeah? Are there different slopes? Are there different kinds of hills and different slopes? Okay. How can you, let's describe, what kinds of slopes or hills? What other words would you use to describe different slopes?
Some slope are very steep.
Okay, steep. We have steep. What is steep? You said very...
Yes.
Okay. Good. What else? Mike had one going like this. Is that going down?
Almost. But
Almost flat. So we have a flat slope, which is sort of, doesn't mean much. And then if we have like a gentle slope, maybe you can call it gentle or also shallow. A shallow slope. Hey, shallow. Yeah? So we can have flat, shallow or gentle, and steep. We know this from everyday life, yeah? What kind of slope would you prefer to walk? Huh? Flat, okay. You don't want to go up. What about if you're going down? What kind of slope do you like? Steep. It's nice to go down a steep slope. And you're just falling, right? Or shallow, maybe shallow. Steep might be dangerous, so okay. Not too steep. Okay, so we have different grades. Sometimes if you're a truck driver, they call this grade, the grade of the road. Is it a flat grade or a... But we're going to call it the slope. So it can have a flat slope, which is it's not going up and it's not going down. It's just flat. Or it's going up a little bit. Of course, if you're walking this way, then it feels like more work. If you're walking down, then it feels very nice, right? So let's say to go down, we're going to draw it like this. You can go down like that, and you can go down here and up there. So we're always walking to the, if I draw them on the board, we're going to say we're always walking that way, towards the positive x. We're always going to walk in the positive x direction. And if I meet a line that is going up, then I'm going up the hill. And the steeper it is, the more work it takes, right? The more effort. And so we might say, well, this, and if it goes down, then it takes less. I know, if I'm on a bicycle, I can just do nothing and the bicycle will go. Yeah? On a flat, I have to pedal a bit. If I'm going up, I have to pedal more. And if it's going down, I can relax. And if it's like this, I can really relax. I might even have to brake, yeah. Okay. So, we're going to make a connection between this idea of walking on hills, or bicycling on hills, and lines on a graph. Because what have I drawn? Here we were thinking about hills, but what we drew were lines, right? And the lines they have some differences, and the difference is how much of an angle they have, what their slope is. So when we talk about the slope of a line, what we're talking about is exactly the same thing. Is it a little bit or more, or is it going down? So this number is a measure of how hilly, what kind of hill is my line. That's what the slope is. It's nothing else. This number simply tells us that is this a little, is it flat, is it gentle, or is it steep? So now let's give some numbers to these lines, right? So here I said, and you asked, I says, okay, if you go over by 1 unit, then you go up by 2 units. So mathematically, we need to have sort of a definition for slope. So the definition we will use is that slope equals delta y over delta x. Now, do we know this symbol delta? What does it mean? The change in y. So here, and obviously this has to be between 2 points. From this point to this point, for example. So what is the change in x from this point to this point? Is 1. What is the change in y from this point to this point? From here to here, it's 2. So we have 2 over 1, which is 2. So my line has a slope of 2. Let's draw another line and calculate its slope. Let's say I have a line that goes like this. Yeah? It's not, this is a steeper hill than this one. Do we expect the number to be bigger, smaller? What? For the slope of the red line. This number will be smaller. Will it be negative? No? Okay, let's find out. So let's start here. This is the point 0, 1, right? And let's go here, which is the point 1, 2. X equals 1, y equals 2. And let's calculate our slope. Delta y over delta x. What is the change in y from here to here? You always go from left to right. We're always walking in the positive x direction. So you always start from the left point to the right point. From the left to the right. So then what's the change in y? From this point of y, from here to here. Did I go up or down? How do you get minus 1? 1 what minus 2? Which? Come show me. Yeah. Is this, yeah. So this is the rightmost point. So we go 2 minus, this is the left point, minus 1. And then delta x is the right point, which is this, which is 1, minus the x of the left point, which is 0. This is equal to what? 1. 2 minus 1, 1, over 1 minus 0, 1, 1 over 1, 1. Good. So we have a slope that is half of this one. Okay. What about now if we have a line going like this? That wasn't perfect, but it's going through these points. So again, we're going to go delta y over delta x. The change in y over the change in x. I'm just going to put it over here. Delta y over delta x. I didn't explain before what is this delta. Huh? Delta in math, we need many symbols. Yeah? So we have A, B, C, D. We have the letters of the alphabet. We have some symbols like plus, minus, equals. Okay? But then we needed even more symbols. So what people did is they said, okay, we're running out of the letters of the Roman alphabet, which is A, B, C, D, what we use. So they used the other alphabet that they knew, which was Greek. Greek has an alphabet similar to Roman, but a bit different. And the letters look different and they have different names. But the sounds are similar. So in Greek, instead of A, B, C, D, we have alpha, beta, gamma, delta, epsilon, and so on. And the capital versions, I think that's alpha. What's capital beta? I don't remember. It might be like a B. Gamma is this. delta is this, capital epsilon is, I think, a big E, and so on. And then you get some other. Pi is in here, by the way. Your old friend pi? You know pi. Pi is the letter P in Greek. It's not a made-up letter, it's the letter P in Greek, called pi. So we're using delta, which is D, the D sound, for difference. We said the change in, or the difference. So this symbol, it looks like a triangle, and it is the capital D in Greek. So it means difference. And in math, we use it to mean the difference, the change in something. So, back to our calculation. So we have 2, what's the point, what's the coordinates of this one? 2. What's the coordinates of this one? 2, 0. Okay. Can we do this calculation now? So remember, we always take the point on the left towards the point on the right, which means to know the change, it's the point on the right minus the point on the left. Yeah? So what is the y value of this one? This is P2, this is P1, so we go y2 minus y1 over x2 minus x1. So what is that? So y2 is the y value of point 2, which is 0, minus the y value of point 1, which is 2, so minus 2, divided by x2 minus x1. 2 and 0. So notice that the x down here will always be a positive difference, because we're always taking the right minus the left, and the right is always a bigger x than the left, right? My board is getting full. Yeah, if I say you're here and you're going here, yeah, you've moved from left to right, how much is the change? So this is the number 1, 2, 3, 4, 5. Here you're at the point 5. Here you're where? 7. So in order to go from 5 to 7, what did you add? 2, not negative 2. You added 2. Yeah? So this distance is a distance of 2. 5 plus 2 equals 7. Now, you can remember at the beginning of the class, if you don't know this number, you know 5 and 7, how do you get 2? So if you're going in this direction, the way you calculate the difference is you start with the last number and you subtract the first number. That gives you the difference when you are going in that direction. Because I have said we always go, this is a math, a convention, right? Everywhere in the world, in all of math, when we calculate the slope, we're moving from the left to the right. So we're going like this. And that means we take this one minus this one to get the difference. Yeah? It's a good question. I hope everybody is clear on that, yeah? Okay. So then this is equal to what? So we said the y value here is 0 minus 2 divided by 2 minus 0. X is 2, x is 0. So the answer is what? Minus 1, yes. Thank you. I was about to write minus 2. Minus 1. So this had a slope of 2, we're going to use m for slope. M was 2. Here, m was 1. Here, m is -1. Okay, so now we start to get an idea. Okay, if my hill, as I'm walking this way, right? If I have to go up the hill, then it's a positive number. And if it's a big steep hill, then it's a big number. Right? It takes a lot of work to go up that hill, so we get a bigger number. If I'm going down the hill, then actually I have to brake. So now, if I'm on a bicycle or on a car, so now it's a negative number. I have to actually, yes. Another word for slope is gradient. Gradient. Now, so we have given some numbers. Here we said we have positive numbers for these ones. These are small positive numbers. This one is a big negative number. And when you're going down, then it's a negative number. Now, what do you think is the number for the flat slope? What do you think is the number, what kind of number will be for a flat slope? 0. It's not going up, so it's not positive. It's not going down, so it's not negative. Well, what number do we know is not positive and not negative? 0. So this one is 0. That's the slope of a flat line. And we can check. Yeah, we can take here. This is a line, yeah? It's flat. Here we have coordinates 5 and 0. Here we have coordinates 7 and 0. Yeah? So let's calculate our slope. It's the change in y divided by the change in x. So what is the change in y from here to here? It's 0 minus 0, okay? 0 minus 0. We can see where we're going. And then change in x, 7 minus 5, which is equal to 0 over 2, which is 0. The slope of a flat line is 0, always. And now we have a way to think about all lines. All lines have a slope, and the slope basically tells me, am I going up or am I going down? Always when looking towards the positive x direction. Am I looking up? Am I looking down? Or am I going flat? And if I'm going up, am I going up a lot? Or am I going up a little bit? Am I going down a little bit? Or am I going down a lot? And that's the slope. That's the meaning of this number, slope. Now, we're about to close. Where we are going with all of this, now you might say, but sir, why do we need to talk so much about slopes? Because what we are interested in is more interesting. You know, a straight line is fine, but it's not very interesting. It's a straight line. You write y equals 2x plus 2 and you're done. What more do you want? Yeah, I can do some algebra and I can tell you anything you want. So why are you bothering me with all of this? And the reason that we are bothering with all of this is that we are also interested in more interesting functions that are not lines. Maybe we want to work with a function like y equals x squared. Yeah? Y equals x squared, it looks like this. It's a parabola. Now I ask you, what is the steepness of this function? How steep is it? What is the slope? And you look at this and you go, well, it changes, right? Here, it's like this, but then it becomes like this. It's going down. It's a downhill, but it's not as down. Now, here it looks kind of flat right at the bottom. And now it's starting to go up. So what kind of question is what is the slope of this thing? It doesn't have one slope. It has all these different slopes. Now, is there a way to calculate the slope anywhere on this graph of this function? Yeah. Most hills are not straight hills. Yeah. If you're an engineer, you have to calculate, okay, the mountain is going up like this, and then it's going like this, and then it's doing this, and then it's doing this, and then it's, yeah. The world is not straight lines. And the same is true in economics, and business, and all sorts of fields. Some things are linear, but many things are not linear. But we still want to know the slope. We will discover what does the slope, right now we just said the slope is how steep it is. Depending on what you are graphing, what is the function about, right? It can mean something. It can be a graph of distance traveled. It can be a graph of production in economics, a graph of consumption. It can be the growth of an asset, right? You're investing, the example we just saw. And then the slope becomes a measure of how fast is that changing. So how fast is my investment growing? Or where is the maximum profit? Should I produce this much or this much? Where is my maximum profit? And to do that, you need to look at the slope. But if your function is not aligned, then what is the slope? And that's what calculus is for. How do you find the slope of a function that is not aligned? So we will end there today. Next week, we will start on limits, which is how we begin to find out what is the slope of a function that is not aligned. Okay, I'm not going to give you a problem set this week. Those who still have to finish some previous ones, this is your week to catch up. For those who don't need to catch up, I will recommend, you don't have to submit it, but I will recommend that you review, which one? I think this chapter 1 on functions and graphs. This is now the other textbook. So far we've been using, where did you go? We've been using this one by Ian Jacques, which is Mathematics for Economics and Business. We may still use it at times. There is a chapter on differentiation here. But we're now going to switch over to this Calculus Volume 1. It looks like this, the cover. So next week we will begin on Chapter 2, Limits, and you will find it helpful to review Chapter 1. Especially 1.1, 1.2. We've done some exponential and logarithms, so now these functions should be more familiar. Have you studied trigonometric functions before? The sine function, the cosine function?
Yes.
Yes? Okay. So that's trigonometric functions. You can review some of that. And then inverse functions. An inverse function is simple. Yeah, you can review that as well. It'll be good. There's a glossary at the end of the chapter. So if you need a reminder, what do the different words mean? They're all defined somewhere in the chapter. And there are some key concepts. So if you want a quick, what are the key ideas in each of the sections of the chapter? And then maybe decide, oh, let me go read more about this or this. Then you might want to start here from the key concepts, which is inside the glossary section. And then there's lots of review exercises. And I mean, lots. From 310 to 336. So 26 questions, 27 questions. So you may want to try some of these as a way to also keep practicing. But there's no problem set to hand in this week. All right. That's it from me. Thank you all. And I have a thought. Would you... I'm not sure if it's a good idea, so I just want to get your sense. If we, instead of having 2 hours once a week, if we met for a shorter time twice a week, would you want that? You prefer to have your brain completely melt on one day and then... It's okay like this? Okay, that's fine. No, for a shorter time. Maybe an hour, or an hour and a half, an hour and a half. So, when we meet next week, if you have some more thoughts about that, you can share. Yeah. Oh, attendance. Yes, sorry. I have to write. Today is the 7th. And it's 1 to 3 p.m. There you go. And we can, let me just turn off the recording.